So here we've got the fundamental theorem of calculus part 1. The derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. So the first thing that I want to do is convince you that this constant a at the what we call the lower limit of the integral, just because things aren't confusing enough, the names of these two variables, they're called the lower limit and the upper limit of the integral. This is the upper limit. So not to be confused with the limits that we were talking about, limit as x approaches something. This is called the lower limit of the integral and the upper limit of the integral. This lower limit constant a is completely irrelevant to this result and doesn't matter. So I'm going to do a little bit of work to convince you why that should be. So number one, geometrically, what does the derivative of the integral from a to x mean? It means we have a picture like this. I have the area under a curve of a function f of x. Right, and I'm going from a to this x. X is the variable, so the variable x is changing. So so this question, what is the derivative with respect to x, means as the x changes, how does the total area change? Well, where the area started from doesn't matter, because the question is about how the area is changing as I add on little bits more. So adding on little bits more here and looking at how the total area changes is not going to be affected by the starting point of the area, because that's just constant. All right, so that's a geometric way to express that. Here's a little bit more analytic way to express it. So let's say which is to say this. Suppose I took a different constant at the bottom, integral from b to x of f of t dt. All right, so suppose I just take a different variable from a. It's a different constant, actually. So then, consider if I had, some function, and here's a, and here's b, and here's x. All right, so then the integral from a to x of f of t dt is equal to, all right, so a to x is, I'll highlight these a little bit. Here's the integral from a to b of f of t dt. There's f right there. Here's the integral from b to x of f of t dt. So the integral from a to x is equal to the integral from a to b of f of t dt plus the integral from b to x of f of t dt. All right, and then I can just sort of rearrange those a little bit and get that the integral from b to x of f of t dt is equal to the integral from a to x of f of t dt minus the integral from a to b of f of t dt. All right, so another way to say that is that this integral a to b is the only difference. This is the only difference between the integral from b to x and the integral from a to x, is this amount here. All right, but this result is not about the areas, it's about the rate of change of areas as the x changes. So if I do a derivative with respect to x on all sides, all right, integral derivative with respect to x of b to x of f of t dt equals the derivative with respect to x of integral from a to x of f of t dt minus the derivative with respect to x of the integral from a to b of f of t dt. All right, and so here's what's important about this. The integral from a to b, we'll just highlight that in green. The integral from a to b is constant with respect to x, right? As x changes, the integral from b to x is changing, the integral from a to x is changing, but the integral from a to b is not changing when you change the x. Therefore, this is constant with respect to the variable x. So its derivative is 0. Therefore, the derivative of the integral from b to x of f of t dt is equal to the derivative of the integral from a to x of f of t dt, all of which is to say that it doesn't matter what the bottom limit is. I'm going to get the same derivative. I'm going to get f of x regardless of what that lower limit is, because I just put two random numbers a and b, and I just said for any two real numbers a and b, these two derivatives are equal. And it really comes down to the fact that in any case, you always are going to have a constant amount that's not changing. And what the ddx is about the part that is changing. The a is not changing with respect to x. Therefore, it doesn't affect the derivative being the function f of x. All right, so we're getting very close to being able to do something useful here. I'm sure you guys have been very patient. We're like, when are you going to do something useful with this? It's coming. All right, so here's the next thing. Let's see if I can see where I'm at. Yes, okay. So now let's look at the integral from a to b, or the area from a to b under a curve. And the same thing. All right. So here's an area that we're interested in, and that integral is the integral from a to b of f of x dx. So am I going to go t here? Yeah, I'm going to go with t here. F of t dt. All right. So what we do in order to get the next result is we're going to look at, remember in the theorem, the lower limit is irrelevant. So I'm going to take advantage of that, and I'm going to pick an arbitrary lower limit. In fact, I'm going to pick 0. All right, so I'm going to go over here to 0, and I'm going to look at the relationship between the integral from 0 to a to b, and 0 to b. So what I'm going to have is that the integral from 0 to b of f of t, all this is just geometry, it's just about adding the areas. The integral from 0 to b of f of t dt is equal to the integral from 0 to a of f of t dt. But like they like to break this down on the AP exam and look at, you know, little, like they'll just give you some areas and have you draw a conclusion about how the sum of the integrals, how the sum of the parts has to equal the total. That's all this is saying. The total area 0 to b is equal to the sum of the parts 0 to a plus a to b. That should make sense. All right, but then we're sort of play around with them algebraically, because what we're really interested in is the integral from a to b. So the integral from a to b of f of t dt is equal to the integral from 0 to b of f of t dt minus the integral from 0 to a of f of t dt. All right, that's just solving this equation for integral a to b, because that's what I'm interested in. Now, what I've got is this nice relationship with the fundamental theorem part 1, where, somewhere, all right, the derivative with the x on the top is f of x, regardless of what is on the bottom. The bottom is 0, that is arbitrary, okay? So what we now know is that this is equal to f of b, where f is an antiderivative of f, minus f of a, where f is also an antiderivative of f. And this is called the fundamental theorem of calculus part 2, sorry. But let me add in where f prime of x equals f of x. Another way of saying that is f is an antiderivative of little f. All right? So, yeah, do you want to say anything more about that? No, but this is fundamental theorem of calculus part 2. Fundamental theorem of calculus part 2. Often just called FTC 2. Do be aware, some texts change that definition. And this is what it is. All right, the integral from a to b is capital F of b minus capital F of a, where capital F is an antiderivative of f. Okay, now we're ready to see how this helps us to actually evaluate integrals. So if we come back to our famous area that we started with, we can now call it the integral from 0 to 2 of x squared dx, right? That represents the area from 0 to 2. This area in here is the integral from 0 to 2 of x squared dx. All you have to do is think of a function whose derivative would be x squared. Can you think of a function whose derivative would be x squared? When we think of that, we know this is going to be capital F of 2 minus capital F of 0, where capital F prime of x equals x squared. Well, the derivative of x cubed over 3, the derivative of x cubed over 3 is equal to x squared. So that's our f for this problem. So that means my integral 0 to 2 of x squared dx is equal to 2 cubed over 3 minus 0 cubed over 3, once again, 8/3. All right, so this is the quick way to get this integral, but we can make it even better, so that's what we're going to do next. We're going to generalize this to other functions and see how we can sort of quickly get these antiderivatives.